tonight I'm not going to talk as a person from AEMO. So I'm talking on behalf of IEEE Power and Energy Society as a board member. Can we see by show of hands how many IEEE members we have here? Okay, not so many. So IEEE is the largest engineering organization in the world. Close to 500,000 engineers are members. Power and Energy Society is one of the 39 societies in IEEE, and we have about 38,000 members globally. So what we do here is the views of IEEE. What I speak here is the views of IEEE, not necessarily views of AEMO. So that's the first thing. If you want to become a member, it's very easy. You just need to see me outside this room. And you know, the publications of IEEE publishes most of the engineering standards in the world. And the magazines we publish are the most relevant to the industry, especially in the energy transition, you know, the topic of interest that we have. And membership is not expensive. Membership is just $190 per year. And if you don't get anything just to get the magazine and read it, I think that's worth it, the membership fee payment. So that's the first point. The second point is that I think the narrative of what we talk about in energy transition has evolved. So, well, I'm hoping that I say something new to you, because you know we have been talking about energy flows now. It's two ways. You know, PV are creating challenges. All of this, we all know that. My focus is not this. My focus is trying to make a case for solutions rather than stating problems. But because I have a wide audience, very briefly I touch on challenges and problems and then quickly shift to solution mode. Because I don't see distributed energy resources as a liability for power system. I truly think that DER can be an asset to the power system. It's just our choice of how to deal with them. So with this brief introduction, I go to my first slide, and I want to show you this beautiful photo. And let's take a moment and think. Only 2 minutes of energy, solar energy that reaches the earth, is enough to power humanity needs. So there is a lot to still be captured. And I'm not talking about electricity, I'm talking about transportation, about heating, about cooling, about whatever you think of in the space of energy. So we have only scratched the surface, and there is more to come. So there is no point in becoming somehow guarded against this new source of clean energy. But introduction of this in our system means that power systems are changing now. We have fundamentally changed the way power system has been designed and operated. So what are these changes? Here you can see the mix of generation from 1970s up to now. Clearly you can see the rise and fall of nuclear. You can see the rise and fall of oil. You can see a start of fall for coal generation here. And you can see green shoots of different type of generation. And this blue and yellow are going to grow. By 2050, we will have 62% of renewables in the system. And this means a lot for the power system, how it has to adapt and evolve. So drivers for change, of course, started with policy objectives of governments wanted to decarbonize the system. And suddenly, you know, we saw the growth of DER to the level that nobody expected. They are now everywhere. In the NEM alone, every day there are 15 megawatt of DER that are connected to the system. And then advancement of technology. Technology has enabled a lot of things that previously wasn't possible. And customers. Now customers not only want to know where the energy is coming, they want to know how they can make changes, how they can make choices for their energy use, their consumption, and how they can be a player in this field. They didn't act like that before. And Australia will be leading. This graph shows the ratio of decarbonization of electricity systems in the world. Most of places that distributed energy resources are very active. You can see we are somewhere here, and in this graph, Germany is leading. But very soon, Australia will be leading. And these guys, Bloomberg, who put this together, only looked at the NEM. If you put Western Australia here, then the graph will be even more leading. So I thought when I put this presentation together, I thought which systems in the world we can learn from. And Hawaii is a system that's pretty much is an island system, a lot of distributed energy resources penetration. But I tried to look at some other figures, you know, economic figures, where Hawaii is compared to Western Australia. You can see the difference between GDP of Hawaii and GSP of this state. I tried to put them on a graph. Do you see Hawaii? So the risks are really magnified. We run a system that it is so important to the economy of this state. And there is almost nobody to learn from. So we are really leading here. So we need to come up with new ideas, and we need to be adopting new ideas. My role is to run the power system. So I want to give you a captain's view of what I see. Are you ready for it? You know, when you're on a plane, the captain comes and says, sit back, relax, and enjoy the ride. So this is something like this. Let me give you the view. You can see no uncertainty is rising. Previously, the weather only affected the load. So our planners knew when the temperature was up, the load was up. When we were in the middle, the load was low. When temperature went down, the load was up again. So it was easy to predict, easy to forecast. Now, both sides of the supply and demand equation depend on the weather. On the right-hand side, you see a graph of one PV system during the year. So you can see it can be everywhere. From here to here. The average won't help because we are running a power system. For us, the output in real time is very important, and the output can be anywhere. Volatility is rising. So previously, the generators were dispatchable. You knew when you dispatched them to a point, they could more or less stay at that point. But no, generators look like this, and they're very volatile. So you can see in this graph the output of rooftop PV in the SWIS. You can see the output of the wind, and this is the load. So wind can do one thing, load can do another, and PV is there. Volatility is rising. Just last week, we had 600 megawatt, more than 600 megawatt of change in one dispatch period in about 30 minutes. 600 megawatt. So if you can see, this is the wind, and this is how quickly can come to zero from their output. Control is diminishing. This is a graph of the sum of PV output in the SWIS. And you can see some days the uncontrollable component of generation is more than 40%. So we have, your captain has very, very little visibility on the control that it is in front of him. Most of it is uncontrolled. Resiliency is deteriorating. Power systems are becoming less resilient to things that impact them from outside and inside. Very recently we had blackouts in UK, we had blackouts in Argentina, we had blackouts in Indonesia. Resiliency is the new subject. Previously we didn't talk about resiliency, but there are so many working groups in the industry now talking about resiliency and how it is affecting the power system. Extremes are becoming norm. This is the advice from Bureau of Meteorology, and they are saying increased frequency, intensity, duration, and extent of weather events. So they are forecasting this. Markets are reaching their limits. This was Saturday, 12th of October. We reached the bottom price floor in the market, minus 1,000. Something that those people who put minus $1,000, they never thought that this will be reached. But if I say markets are starting to show that they are not working, I'm not too wrong. In April, AEMO put together a paper saying that markets will reach into market inefficiency very soon, and we are showing the signs of this. And these events become like the norm. I remember in 2016, my forecaster came to me and said, oh, last night, today we had a low that compared to last night was lower. This is the first time it happened. And then it happened again, and again, and again. And if you put a graph of how the load during the day has been lower during the night, it is now an exponential graph. So it starts with one occasion and then becomes the norm. So I'm saying that we are running out of runway. But up to here, that's enough of the problem. So we need to come up with a solution. That's what matters. Power systems are a system of complex systems. It's very complex. Actually, the level of sophistication of the power system is what we call ultra-high scale complexity, because a power system contains multiple systems that interact with each other in many complicated ways. It has elements that have conflicting objectives. It has systems that work together but interact with each other in many different ways. So power systems are very complex, and in order to understand how they work and how we can come up with solutions for the problem that we have, we will need to know many things. We need to come up with a vision. This is the way power system were working like a decade before. So you can see it is relatively complex, but not as complex as how they are now. There are many, many more elements. At the turn of the century, I think in 1990s, there were about 100 generators in Australia. in 1990s. Now about 2.3 million generators. So how this amount of complexity can be worked through, that is the challenge. So how are we going to manage? How are we going to manage this situation? There is a saying that says, to every complex problem, there is a neat, clear and simple solution. Do you agree? Which is wrong. Unfortunately, there is no simple solution. The solution can be also very complex. But I think we can get through it. The vision about the future of power system is also very complex, because power system involves power engineering, involves control theory, which deals with controlling elements that are constantly changing over a long period of time, in real time. It involves network theory. It involves systems theory. It involves system structures and system architecture. It involves software engineering and optimization theory. So these are the technical parts. On top of them, it involves economic theory. It involves policy objectives, rules and regulation. So a vision for the power systems should include all of that. So a holistic approach is required. I like to rhyme things up, so I'll give you two rhymes here. So from turbine to toaster. So that is how optimization in power systems should work. You can't just focus on one part of the power system and say, oh, we'll fix this part. It won't work. It should be from turbine to toaster. It should be from generator to, what rhymes with generator?
Refrigerator.
Refrigerator, thank you. So a holistic approach is required in the power system. If we look at the power system this way, we may have a chance. So what are the other trends? We talked about decarbonization, decentralization, and then there is digitization or digitalization. I don't have time tonight to talk about sector coupling, but that is also another topic of discussion which is very important. We are in the age of big data, and there are big energy data that currently we get, and they are accessible from smart meters. Smart meters continuously give us data points about what's coming, what they can measure. We have SCADA, system control and data acquisition, that every 4 seconds there are thousands of data points that reach to us, and we need to make a sense of it. We have phaser measurement units in the power system that constantly send data and information. We have sensors, IoT, EIoT. Let me explain EIoT and IoT a bit later. And then, artificial intelligence, machine learning, and deep learning. So here, I would like to talk to you about big data analytics in energy industry. Whatever we can gain from our input, things like weather data, things like load data, GDP, electricity prices, can turn into very complicated and insightful analysis. This information can be clustered because we can't just deal with all this amount of information as a whole. So we cluster parts of this information to understand how trends are working. Power system is a very complicated system, so normal machine learning probably will not be sufficient to understand the complexity of the power system. We need deep learning. So the difference between deep learning and machine learning is that in machine learning, the machine can get the structured data and then learn based on that. Then machine can understand, for example, the difference between a road and a bridge. But this is very simple. In deep learning, the machine works like a human brain. It can get data in unstructured form. It can get data from different sources and different layers, and then can make sense of it. And then we can make feature extraction to understand the trends and do something with it. The objective will be enabling renewable energy integration, because that will be the future. So whatever we do here will ensure that renewable energy can further integrate into system and we can increase their share. But we can do it securely, such that the power system remains secure. Do you know what this is? It looks like a time series photography or of cars with lights on during the night, but it's not like that. This is the heat map of sensors. 2 years ago, an Australian university student looked at the Middle East and looked at an application that received data from the sensors. This is in Syria. It was like pitch dark, and then suddenly he saw this. And he said, oh, this must be a military base. This is a secret military base, US base. And the people who had these watches, you know, the watches that track your activity, they had them on when they were running. And these sensors continuously transmit data to internet. This is the era of Internet of Things, because there are so many sensors now that continuously send data to the internet. And these sensors tell something. So if you have a mobile phone, most likely your mobile phone have more than 10 sensors. And these sensors send information to the manufacturer of what features you are using, how you're using your mobile phone. And manufacturers use this data to understand what features need to be improved. And they continuously improve the product. So in our industry, we are not using a lot of technology that is currently available. I'm so excited about this Internet of Things, because I looked at, okay, how can we create a situation that power system can continue to be secure while we decentralize it? And Internet of Things is really one great solution, because Internet of Things was originally put together for supply chain management. So they wanted to know how much product is there, how much they need to produce, what are the conditions of the product handlers, you know, the trucks, everything. So they put together these sensors that they are not so cheap, such that they could trace this supply chain and put together measures to be in time. Energy is effectively a supply chain issue. So it needs to be consumed as it is generated, or it needs to be stored. By application of Internet of Things into the energy industry, we can create a supply chain management for energy. This is not future, this is now. Really, the technology exists, and technology is so cheap that in your home you can have these sensors connected to all your devices. And when these devices send information to the internet, these information can be used to manage this supply chain issue with energy. This is the application of Energy Internet of Things in Europe. This company is using that information, is using exactly this sensor information to ensure there is flexibility in the load. Maison is working with some European utility to understand how we can respond to the volatility that exists in the generation now by orchestrating the load, so creating load flexibility. I wanted to talk about the rate of adoption of technology. You can see here, it took 75 years for 50 million people to take a telephone. 68 years for airplane, 62 years for cars, and you can see, this is multiple decades took for 50 million people to take up different industries. But when it came to internet, suddenly this time frame is much, much shorter. So you can see for Pokemon, it only took 35 days. And this is how internet has created this connectivity that can connect everything together, can shape up the future. And my question to you is, how much of this are we using now? I'm sure you've heard of Industry 4.0. This is the fourth industrial revolution that has happened. The first one was the steam machine, second one was electricity grids, which enabled mass production. Third one was IT and computers, and the fourth one is all about connectivity. It's about cloud computing, it's about IoT, and I would say it's about EIoT, which is Energy Internet of Things. If you look at our industry, we are not using much of it. So we have let distributed energy resources to transform this industry, but we are not grabbing the solutions. I'm not sure if in your company, how many people are working for your innovation department? Is there any such a department even? So there is a lot to be adopted, and I hope that the rate of adoption to change is enough to manage the complexity and challenges that we have ahead of us. But then I'm happy that we live in a state that we have the ingredients for the solution. So we have the DER roadmap, which we need to really think about how we can turn it into a grid modernization strategy. Because we have short-term technical issues to address. These are the things that I mentioned before. We have medium-term integration issues. So these medium-term integration is about how we continue to integrate renewable energy into our system. And it is not about how they can effectively work now or efficiently work now. It has to have a solution for how they can evolve into the future and how they can evolve such that future power system is secure. So the principles, of course, it should be customer empowerment. That's the first thing. But then I say 2 S's and 2 R's. So safety, security, reliability, and resiliency. These are very important. And we need to look at power system as a whole. So we have a whole of system planning program in Western Australia now. From turbine to toaster, do you remember? And also grid and market platforms. Why we are talking about platforms? Because we don't have the energy, we don't have the capacity to do everything. Western Power won't have the capacity to do whatever needs to be done. Synergy won't have the capacity. We need to create platforms that others come in. Others who are innovators rather, and can come in and change things. If we put the right customer protection in, the right framework in, and let the industry innovate the power system. And then we need to optimize this, because of course, optimization is also a goal. And we need to ensure that the right cost allocation is in place. So implementation will be very difficult because we have legacy systems. So we have so many 250,000 people who have DER with old inverters. Probably we can't do much with them. So we have to live with them. But then the new standard will ask for autonomous operation of these inverters. So the new ones will have better. We need to come up with a combined solution of how to operate the legacy system, but then how to operate the new ones that can be remotely controlled. So the platform can include the cyber physical assets and include also communication technologies that can be part of the future grid. I said markets. One of my colleagues who is well aware of this energy transition situation, I can't see him here, but he said once that be prepared to change your mind. And I have changed my mind. I wasn't a person who was much in favor of the markets. I've seen so many market failures. But with distribution market, I'm really believing that it is something that can change this, and it can make a great impact in the right direction. So in the influx of distributed energy resources, we have focused on two things. We have focused on environment, and we have focused on customer value. We have missed one thing. Do you know what that one thing is? That is power system security. A power system needs all three of this to run securely. So how can we bring this back into the equation? I really like this slide. Let me talk to you about what I mean by PTU, prosumer to utility, and prosumer to prosumer trading. Currently, the PV systems in this grid, what they do, they start generating, and the energy steps in like imagine a confined room that a giant steps in every morning and pushes everything out. And then towards the end of the day, it just disappears. So this is what we are facing every day. The PV energy that is appearing in the grid is so large. You see how much it was, about more than 40%. And this energy does not meet the reliability standard that we have here. So what do we do with this? As the system operator, we ensure that this energy meets the reliability standard by massaging it into what the code wants us. So the reliability standard asks for almost 100% reliability. There is only 0.002% of unserved energy. So we turn it into a reliable energy and we give it back to the customer. And in doing so, what we do, we erode the value of local consumption and also erode the value of the generators that provide this service. The point that I was convinced the distribution market is required was very clear. First, customer value. Currently, who has PV in their roof, in their house? Okay, almost half. Well, you're not very representative of SWIS customers. Currently, 250,000 people have rooftop. If all of them were like you, then we would have much more problem now. But let me say something. For those of you who don't have, I guess you're either renters or you like to look at your roof like your roof tiles, or you're a tourist here from overseas, or you never took 5 minutes to think about it. Somebody told me also one option is clinically insane, because the return on that investment is now only 3 years for most of us. For me, I calculated it was 2 years. So, but please don't rush to put a solar PV on now. Why do people do that? Because the only price they compare is the price that they get from the utility, 28.28 cents per kilowatt hour. Put it in Excel file, you can see that it makes a lot of sense to put a solar PV on your roof. That's why we have this problem. But if we liberate the market such that I can trade with you, you can sell to me at lower than this price that Synergy can sell to me. And then suddenly, if I can buy from you 10 cents, then the business case doesn't stack up. Instead, I will go and invest in a storage. So this is very simple reason why liberating this market for people to trade between each other can help the security of the power system. I went in my house and took photos of all my appliances. And I thought, okay, how much each appliance needs reliability? Because the new generators, all are volatile. They don't have 100% reliability. So you can see these are the appliances. The wet appliances that they don't need 100% reliability. My computer, if I run on battery, I can run for 2-3 hours. Doesn't need 100% reliability. The air conditioner can tolerate a bit of reliability, poor reliability, if I may say. You want to see the light come on when you switch the light, and you want to cook, you need 100% reliability. And when you watch TV or you want to heat up something. So if I can categorize them into the sort of reliability that they need, I can say these appliances need 100% reliability. They don't need, so they can tolerate 80% reliability. These ones can tolerate 60% reliability. For this, I don't mind. If the pool pump is running at night or during the day, it can run whenever there is energy. So if I opt for lower reliability, and then I can get a cheaper price because of this, then we can maximize the consumption of energy where it is produced. And this is a great thing for the investment in the grid. Because Western Power will not have to put another transformer, because all of us are starting to consume at the same time. So this is how we can create a system where the load actually becomes flexible and goes with the flexibility of the generation. And if a market can facilitate that, then the prices will come down, because I can opt in for lower reliability for some of my appliances and high reliability for others. So you can see that the future distribution market can trade not only on price and quantity, but can trade on price, quantity, and reliability. So we will have a system in future that has two-way flows. Flow of energy and then flow of flexibility. Generation gives the load energy, and the load gives generation flexibility. Let me talk to you about one case study in the UK. This subject of load flexibility is very new. But in UK, they did a study and they found out if they create flexibility in the load, they can save between 3.8 million pounds to 3.8 to 8 billion pounds a year. There is 26% curtailment of renewable energy in the UK, 26%. They can reduce this by creating load flexibility. They can reduce network investment because the energy that is created in a region can be consumed in the same region. And also, there won't be a need for new generators as much as an inflexible load. This is the study they done to look at the market power. Here you can see the load profile when there is 0% flexibility in the load until 10%. So you can see that the load will be much higher. So this is in terms of gigawatt. This is really substantial, this difference. And in terms of market power, when there is a market that has a lot of a business that holds a lot of power in that market, normally markets come up with price caps, or they're trying to increase competition to get away from market power. But with creating flexibility in the load by 10%, you can almost get rid of market power. So I would like to conclude with saying just two things. From tonight, whatever I said, it was focused towards flexible load and also trading liberation. So these two things can save the power system from future challenges. To make load flexible, it takes technology, it takes energy Internet of Things, and it takes a lot of innovation into the grid. And then on top of that, we can create a market that facilitates this. So thank you very much. And yes, if there are any questions, I'm here to answer. Harry.
Thank you, Dean. That was a very broad and big coverage of lots and lots of different things. I just wanted to make a comment. I think they should be congratulated for doing a great presentation. On the TV a few weeks ago, the Federal Minister of Energy was giving the Eastern States power companies a belting because he thinks they charge customers too much. But his statement was very typical of a politician or a person who doesn't actually understand complex systems. His description of it, electricity is a simple thing. You switch it on or switch it off, like a light switch. So the more you can get your messages higher up into the political decision makers, the better for us as a country. Thanks.
Thanks, Harry. I think we have decision makers in this room that probably this creates some sort of impact in their thinking, hopefully.
Change. One of the things you talked about, the change.
Yes.
Change your mind.
Yes, please.
Yeah, you didn't touch on EVs at all, but I think these also could play into what you've been saying today. People always think of an EV as something that is going to be a load, but EVs could also be discharged. And there's been quite a bit of talk about this in recent times, and this could also work to, when we have high demand, people obviously get a better price due to this distribution market, so they discharge part of their car's value, and they get a higher price for it, and then they charge it at a time when it's a cheaper price, so they run their electric car cheaper. But where I see the problem with all this is that if we have a big take-up in the next 10 years, or even the problems we have already existing that will get worse, what I see the problem will be is that the stakeholders moving quickly enough all together, because any particular stakeholder like AEMO, Western Power, Horizon, or the government, they can't just work independently. If they don't move together quickly, we won't be able to implement this sort of technology.
Yes, thanks, Wayne. The PV, I intentionally didn't talk about much because Australia is a bit behind, in the wave of adoption of EVs. Yes, we need to be prepared for that, but first we need a policy, and we need to know, if we're going to have EVs in the future, and should be ready for it. Yeah, currently, unfortunately, we are a bit behind. Peter.
Dean, Pete Kerr from Western Power, thanks for your presentation. Obviously, getting into that situation where you do have greater flexibility of load could potentially be costly. There's a school of thought that I've recently heard that suggests perhaps a different way of dealing with these challenges is to waste energy, to give it away, or to not even to give it away, to throw it away.
Mm-hmm.
Do you ever, do you have a thought on that? Like, is it cheaper for the system on the whole, maybe even in the transition, to just say we're spending too much money on the variability problem? Maybe we need a certain amount, and we give away the rest.
Yes, 26% curtailment in UK of renewable energy. Californian ISO publishes the amount of curtailment of renewable energy every month. So the figures are staggering and growing. When we say costly, you need to also ask the question, who is going to pay? So with energy Internet of Things, the cost is very low. Actually, to put sensors on all your appliances won't cost much. The sensors are, a sophisticated sensor you can buy from $4. And there are companies who will be happy to tap into this value to come and ensure the system is flexible when we enable them to do so. We don't need, I don't think we, as AEMO or Western Power or Synergy, as I said, we don't have capacity to do these things. We don't have, I'm sorry to say, we don't have also the culture of doing these things. And we are not enabled by our regulators to do these things. So there is no scope. The best thing that we can do is to create a framework that others can come and do these things and make innovations in the power system. And such that customers are protected and power system is protected. So we can think about how can we enable that. That's the best thing we can do.
But you won't get change in customer behaviour unless they can see the effect on the price of their electricity. So customers at some point will be paying the market price, and the meters will need to be able to accommodate that. Once customers know what the market price is, they can then program appliances to switch off if the price goes above a certain price, and you can get that flexibility. So surely the smart metering is the first step in that whole process.
Yes, so I agree the smart meter is the first step, but you will be surprised what sort of information you can get from other means, from sensors actually. They can measure almost everything. I think the comparison of smart meters with other measuring devices will be like NBN and 5G. By the time the smart meters are in place, there are other measuring devices that far exceed the value that the smart meters can provide. But yes, I'm with you. You know, the pricing policy actually can change this trend overnight. But it's hard for governments, you know, politically to change policy here.
The customer has to see the difference, though.
Yeah. Yeah, absolutely. From.
Thank you for the great presentation. My question is, because you didn't mention the large-scale renewable energy storage systems like big batteries or hydrogen, is that because you just don't want to take that responsibility and let the distributed cost over the whole consumers? They can buy it for cheap and they can put so many sensors in their houses, so you don't have to pay for that big large system. So if we want to solve this problem, and because we are heading towards 100% renewable energy, we like it or not, so the storage, the large-scale storage, is the key to solve this problem, instead of trying to control every single consumers or prosumers on the SWIS. So what's your comment on that?
Yeah, thanks. I think the solution are in many different ways. My focus in this presentation was on distributed energy resources and what can be achieved through that distribution side of grid. Of course, I'm also excited about the new technologies, hydrogen, you know, how it can be used to store energy, turn into ammonia, and be transported. So there are many different ways to actually use this curtailment of renewables and not let them go to waste. And hydrogen is one of those things. Yeah.
Thanks, Dean. Very good presentation, as said before. It's clear that the network, particularly the network, has not been provisioned for the uptake of solar PV. The planning is appalling. The provisioning of compensation for inertia problems, synchronous compensation, etc. The grid is just growing according to people's whims within the marketplace. So we need to have the government lobbied heavily to cause this transformation to take place. Thankfully, Western Power is remaining in the public hands, because that will allow a transformation to happen quickly. But where do you see the speed of both the uptake of improvements within the network and also the rules to sell some of these services as suggested by some of these other people?
My hope is that our rate of adoption of new technology and new solutions are in a way that we are faster than the challenges that are going to get us. Or the things that can happen to the power system. We didn't discuss other challenges as a result of renewable energy, like diminishing inertia, diminishing system strength in the power system, difficulty with managing voltage and reactive power. So these are also the problems that we have to deal with. And as I said, my hope is that in WA the government is listening. They want to resolve this issue. Really, this is in some jurisdictions the government that doesn't care unless there is a blackout. But here we have the right ingredients to resolve these issues. So I see that we have a chance here. So hopefully we can manage these challenges in time before they manage us. Yeah, sorry.
Just a question about incentives for rooftop solar. If the grid is in fear of too much rooftop solar, do you foresee the adjustment to the incentives to discourage the uptake, or do you see any meddling in the market in that regard?
Well, I hope so. I provided a solution to the government that, you know, the value of the energy that people still continue to sell to the utility until 2021 is something that can be measured. So if you have a solar PV and the time that you're going to still sell 41 cents per kilowatt hour, that's the incentive, can be turned into an incentive for storage. So this way we don't even impose things on customers that they don't like. We give them just a new value. So I'm hoping that somehow some of these policies will turn into better policies that doesn't impose on customers, you know, badly, but are aligned with what the grid really needs.
I'll ask probably a similar question, like, but a different way, which was asked before. Like, the customers, yes, they can modernize probably much faster than what, like, say, Western Power can. But that modernization has to go in both ways. Otherwise, there will not be a benefit, because the system, as is designed now, is designed one way. We're going to distributed energy resources. That system has to be looked at, use Internet of Things and sensors, the way where the energy going to enable that training or production or management of that energy. So how you see that, how because it has to go in parallel. What is the best way to achieve that parallel?
Yeah, you know, future will need a distribution system operator that have fundamentally different tools and different information to manage the system. And I hope the regulation will evolve in a way that will enable the distribution system operator to invest not only in poles and wires, but also in systems, tools, applications, innovation, such that the grid can be managed effectively going forward. You're 100% right. So it can't happen on one side of the equation. It has to be also done by the utility.
Thanks.
I have a question. The IEEE 1547 standard has just been updated last year, and it's gradually being rolled out in the USA. Once they update the testing standards, my understanding is AS 4777 hasn't quite caught up, been updated to that. But I guess that's new standard. The IEEE standard requires voltage and frequency right through. It enables communication to control. Do you think we'll head towards adopting those standards, and do you think it'll solve a lot of the concerns around too much PV penetration?
Absolutely. AS 4777, the future update will even go far beyond IEEE 1547. It will also address a lot of issues that probably IEEE 1547 is currently silent on. Systems like, you know, communication, interoperability. So my hope is that AS 4777 will be a fit-for-purpose standard going forward. Yeah. Okay, thank you so much, everyone. And,